So whenever we decide to plot data, we have to think about carefully what do we put on the y-axis and what do we put on the x-axis. The x-axis belongs to a variable called the independent variable. And what an independent variable is it's a variable whose value is not affected or determined by another variable's value. Let's say you work a job that pays hourly. The amount that you actually work is not affected by how much you get paid. Whether you get paid or not, technically, the hours worked are the hours worked. And you might say to yourself, well, that doesn't make any sense. Well, think about this. Imagine you work 4 hours under the impression that you're going to pay. And then last minute, the boss comes and tells you, actually, we're not going to pay you for those 4 hours. Sorry. The fact that you worked those 4 hours was not determined by the fact that you didn't get paid or got paid. You still worked those 4 hours in the end, even though the manager did you kind of dirty. So the amount of hours that you worked is the independent variable because it's technically independent without you getting paid, meaning it could have happened whether you got paid or not. In the same scenario, though, you also have a dependent variable. And the dependent variable goes on the y-axis, whereas, like we said, the independent variable goes on the x-axis. So if we're thinking about the previous financial situation that we were mentioning about you working for an employer that pays you hourly, well, the amount of money that you're going to see on your paycheck is going to be actually determined by the number of hours you work. If you work 0 hours and your contract is hourly, then you will get paid $0. So here the table shows the cost of student bus tickets, where C is in dollars for the different number of tickets that are purchased. So here on the left-hand side is the number of tickets that are purchased, and then this could be understood as the total gain as a result of the number of tickets purchased. So which one is the independent and the dependent variables? Well, since the cost is based on the number of tickets bought, then the cost is the dependent variable because it depends on how many tickets you buy. So it depends on number of tickets bought. Now, because the number of tickets bought or sold doesn't necessarily get affected by the cost of them, I mean, technically, people could pick up tickets for free. We would say that the number of tickets sold are independent of the cost, at least given the data that we have here. So the number of tickets would be the independent variable. For our second example, it reads as, at the beginning of a race, Alicia took 2 seconds to reach a speed of 8 meters per second. She ran at approximately 8 meters per second for another 12 seconds. So she's at that constant speed for 12 seconds in total. Then slowed down to a stop in 2 seconds. Now I underline that word stop because that tells us that the speed is actually 0 meters per second. Sketch the appropriate graph for this problem. So the first thing we're going to figure out is between the two variables, which are time and speed, which one is the independent variable and which one is the dependent variable? So when we think about time, remember that time still goes on even if nothing moves, which means that it is really independent of any variable. So it is the ultimate independent variable. Whereas speed is literally defined as the distance per time. So speed is 100% dependent on time, so this is going to be the dependent variable. Now, why does that matter? Well, because remember that the dependent variable always goes on the y-axis and the independent variable always goes on the x. So we would know to label the x-axis as time, and then the y-axis would be your speed. And the units for this would be meters per second, and then time would be in seconds. Once we've placed our variables properly, then we choose the proper scale, and then we commence graphing. So we know that time 0, Alicia was not moving at all. So we're going to start at 0, and then it took her 2 seconds to get to 8 meters per second. So if this is the 4-second mark, then at 2 seconds, we're going to put a point for 8 meters per second. And then she continues at that speed until 12 seconds. So we're going to put another point at 12 seconds. Whereby 2 seconds from there, so at 14 seconds over here, she goes to a stop, which is, remember, 0 meters per second. So now I have my points, and I'm going to connect the dots. And your graph should look something like this, where we see a drastic increase in speed from 0 to 2 seconds, then a rather constant speed of 8 seconds until we hit the 12-second mark. And then in orange here, it slows to a stop or a drastic decrease in speed. And I'm going to make that line a little bit better here. Here we go. So this is how we would, from a problem, draw a graph. Remember, the first thing we did was we identified which variable went where, which means which is the independent variable and what's the dependent variable. And then we just plotted the points after choosing the appropriate scale and connected the dots. And one of the easiest relationships that can exist between independent variables and dependent variables is what we call a linear relationship. It's also incredibly common, and a lot of the times we do mathematics to make our relationships at least appear linear so that we can easily read the data. In order for a function to be linear, we need the function to have one x input and one f at x, or one y output. We need all our variables to be to the first degree, not the second degree. And we need the variables to be in the numerator and not the denominator. As well, when we graph our relation, it must be in a straight line. Now, sometimes that line could be horizontal and it could be vertical. But most commonly, if we're looking for a strong correlation or a strong relationship between the variables, we want a slanted line or a sloped line. Lastly, and this pertains to when we're looking at the relationship between two variables in a data set, it needs to have constant first differences. Okay, so let's determine whether this table of values represents a linear function or a nonlinear function. So the first thing that I would say to do whenever you get a table of values is to graph it. Because remember, one of the properties of a linear function is that you should have a straight line. So we're going to plot these points here onto this graph, and then let's see what it looks like. So I've plotted my points now, and if I connect the dots, I should have a straight line. So it passes the graph test. The other test for a linear function is that if it has two variables, which we could see an x here and a y, so there's two variables, so that's check. Is it to the first degree? Well, we need the equation. So we actually can't really tell from the data table, but so far there's enough information or hints that tell us that this is a linear function. Now the fourth one would be, are there constant first differences? And so what we're going to do is, when we say first differences, we're talking about between the y values. So I'm going to look at the y values here. If I look between 4 and 7, that's a difference of +3. If I look between 7 and 10, that's also a difference of +3. And then finally, if I look for a difference between 10 and 13, that's also +3. And so here, I could see that there are constant first differences. And therefore, this is definitely a linear function. Now, those steps that we approached in the previous question don't have to be done in that particular way. You could graph it last. You could do the first differences first. You could do them in the middle. It really doesn't matter. They're all just individual proofs as to whether a function is linear or not. So let's say for this one here, I'm going to take the first differences first and see if it's constant. So I look at the y values, and the difference between 1 and 4 is 3. It's +3. Then the difference between 4 and 9 is +5. And then 9 and 6 is +7. So here, this is not constant. So right now, it doesn't look like it's going to be a linear function because I don't have constant first differences. Now, the next thing I could look at is to whether it's two variables or not, which I could see that there's one x and one y. So this one doesn't check out, but this one checks out. So far we got one property of a linear function and one property that is not a linear function. The next thing we should do is we should graph this function. So once I have my plots pointed here, what I would notice is that if I were to connect all the lines, that is not a very straight graph. Okay, in fact, it's really hard to even connect these two here. So the main point is that this is not a straight line. It's actually a curve. And so this is not a linear function. So there's no constant first differences. It's not a straight line. This is not a linear function. Now let's say, for example, 3 here, we only give you an actual equation. So remember that it's f at x is equal to 3x plus 5. That f at x over here is really just the y output. So it's another way of saying y value. So we're really saying y is equal to 3x plus 5. So we're going to put it to the test. We're going to create a table of values first. So keep in mind that when we're creating table of values, you could really put anything for these table of values. A lot of times people go from -3 to +3, but if you did 0 to 3, that's also fine because it's going to show you the trend that you need to see. So remember that this here is f at x, and we said that f at x is equal to 3x plus 5. So what we're going to do for each one of these x values is we're going to plug it in to this equation. So I plug it in here. Now, when I'm writing f at 0, that's just me saying that wherever the x is, I'm plugging in a value of 0. And we see we get the values here. F at 1 for the 1 here gives us 8. F at 2, where we plug in 2 for x, it gives us 11. And f at 3, plug in 3 for x, that's 14. So now, each of those values, I'm going to put inside the chart. So this was 5, this was 8, this was 11, and this was 14. Now, what I can do is I could take first differences and see if I'm getting a constant first difference. So the difference between 5 and 8 is +3. 8 and 11 is +3, and 11 and 14 is +3. So we have constant first differences, which means so far that tells us that this is a linear function. Now, when I look at the actual equation, I can see here that this is to the first degree. If it was to the second degree, remember that second degree looks like this, x to the 2, and then a third degree would be like x to the 3. But this is a first degree, so that also qualifies as a linear function. Lastly, and this is something that rarely comes up, when I look at this equation here, and I'll kind of write this in lime green, I can see that this x is not in the denominator. And what we mean by that is that it's not written like 3 plus 5 over x. This could be rational and not linear. So the fact that it's not 3 over x makes all the difference. And hence, everything that we've seen proves that this is a linear function, a linear f at x.